Alright, I wanted to show you a cool applet coming out of a different book, and let me go to a pretty simple situation. So here, let me just take out everything. Here's where what we would get out of D field, for example. It's the plot of the solution curves where if we move this blue up and down, we can click and we can get some explicit solution curves, and we can see that they're using green for a stable equilibrium and red for an unstable equilibrium. And it's got the slope field. We can toggle that on and off. And what gets interesting is where we put in all the extra stuff. The phase line, remember, is just a qualitative picture of where are the equilibria, are they stable or unstable, and if I'm here I'm going down, here I'm going up, here I'm going down. And that's the qualitative picture for that one equation. And here's the equation. It's y times 1 minus y. It's minus a, but that's equal to 0. Now this is exactly the simplest version of the logistic model with harvesting, but now we've set the harvesting to 0. So we can play with this slider, and we've seen how that changes things. If you make the harvesting bigger and bigger, then you've got a smaller window of stability. I'm going to redraw the slope field here, and now we've got a situation where there is no equilibrium and all the populations crash. And if the A is really large, then it crashes rather quickly, and there's not anything even close, no hesitation. Oh yeah, I forget, this thing always goes from the left-hand side. It's a little bit different from D field. Now, what else might we want to see? We might want to see, well, one thing this does is it gives you a table, the tabular values if you want. It's not super important to do that, so let's clear that out. But the bifurcation plane, the DE graph, here we go. How would we get this phase line analytically if we didn't have the computer to do this? Well, one way to do that, as we've seen, is graph dy dt, the right-hand side of the equation, f of y versus y. So this is, for a given height, what's the corresponding slope? And we played with that a little bit, and now we can see with the slider, it has a very clear effect. It drags that down. If it's up above, where we have two intersections, we get an unstable equilibrium, where that's the red, and that's always where this line is going up through the x-axis, and when it's a decreasing 0 going down, it gives you a stable equilibrium. And you can see they come together and annihilate each other. Ooh, is it using blue maybe, or some sort of different color? Oh, I couldn't tell. Yeah, sort of a light blue for a semi-stable, which isn't really stable, but it's trying. And then it goes away. Remember, one of the things I mentioned about these semi-stable equilibria is that they're not structurally stable. There is some stability to it that if I take different initial conditions, as long as they're on the correct side, they show up with similar effects. And they all, in fact, it's sort of asymptotically stable on this top. But, of course, one reason it's not fully stable is that if I miss even a little bit on the bottom, it eventually blows up. And another reason why this is not a good kind of stability is it's not structurally stable. That if I just tweak A upward by just a tiny bit, then it's gone. So, and we've seen that there's an even more sophisticated way, another graph we can put in, which is the bifurcation plane, which basically just takes this phase line and just copies it for all the different values of A. And what we can see, the slider takes it and samples all those different phase lines, and if A is 0.25, that's that critical value, that's where you get the semi-stable, and then those things have annihilated each other and you get no stability at all. It's always downward. And then here's the three regions, down, up, and down. So let's look at a more complicated example. Let's do, we did actually a couple of these. Let's do a cubic just for fun. Wait, is this a cubic? Oh no, this is a quadratic, but it's a little more interesting quadratic. Here, there's two parameters. And the way they've set this up, they could actually have like a 3D graph here with A and R and Y, but that would be pretty confusing. And what they've done is they've just said, okay, well, we're just, for each value of R that you set, we're going to look at a different bifurcation diagram. So we want to think of it as like R is the first thing you set, and let's say, okay, let's look at R is minus 0.5. Well, that's not very interesting. Let's say R is 0.25, and let's just fix that for a while, and then vary A and see how that affects things. Here, that's pretty much, it's not exactly translating right or left, but that's the main effect of it here. Yeah, although it is never going to make those solutions cross over the y-axis. And if you look at the algebra of that, that's a good exercise to show that. And so you can see on the phase line how it's affecting, on the bifurcation diagram, how there's nothing really qualitatively happening. The green curve and the red curve don't meet, and the green curve doesn't disappear or the red curve doesn't disappear. They just go like this. They just move in a somewhat nonlinear way. But it's more interesting when right here at R equals 0. Okay, now what happens is that unstable equilibrium, like here there's an unstable equilibrium at 0, and the green comes down and briefly has this semi-stable guy, and then goes past it. And so you do have a crossing and definitely a qualitative change. The change is not in the number of equilibria or what their types are, it's where they are. That green stable one has now come down and just hit and stopped, and the red one, and then it becomes an unstable equilibrium that's moving along. And then if we look at cubics, we get, this is the classic pitchfork diagram here, and we can move it left or right, and we've seen this cubic here. If we change the cubic, that's where you just get 1 0, and then you get a 000 right here, and then it trifurcates into this guy. Bifurcate means split into two. This is really a trifurcation, but people say bifurcate. And here's some cool stuff. If you change it a little bit, then you get a situation rather like what we were doing in class, where this one has just 1 point and then it comes down and produces 3, and it's not that they all meet in a pitchfork, but you have this one that just sails along fairly happily, the green one, and then there's the red and green pair that get created or annihilated. And if you move it this way, it's similar thing, but now the one that's always around is the one on the left side of the axis. And let's see. Yeah, no, that's pretty good. And one more cubic. This one is the classic pitchfork diagram without another parameter. And let's see. Is that all? Yeah. Well, let's see. Here's one more cubic. That's the other bifurcation. That's the other pitchfork which you study. Okay. So I thought I'd show you that. It's pretty cool stuff.